I will ask questions, but some of the answer of the questions are in the slides. Okay. And then there are going to be interactive parts. Hello, everybody. Still some people coming in. So I think somebody lost his phone. Rosalinda has found it. It's a phone with a green case. If somebody is missing his phone or her phone, please contact Rosalinda. She's in the IEEE entrance. Okay, so the last part of today will be a panel discussion called Automotive Ethernet and Beyond. How to connect industries, enable end-to-end communication from the physical layer to the middleware. So we'll discuss about automotive and aeronautics with Kirsten Mateus from BMW, Marc Boyer from Onera, Valentin Kresek from Airbus, and Jean-François Bortolotti from Ampere. So thank you for being here and to accept to be in this panel. So Automotive Ethernet in Beyond. So this year, panel pushes the boundaries of Automotive Ethernet role, not only beyond the automotive industry, but also beyond its foundational layers to full end-to-end communication with a focus on its interaction with both legacy and emerging network technologies. So we have the chance to be in Toulouse, aeronautics city of Airbus, but also from space. So we will try to see how these industries are tackling Automotive Ethernet. So what we know is Automotive Ethernet is a key enabler of software-defined vehicle. It offers deterministic, high bandwidth communication, essential for central computing, zonal architectures, and real-time data exchange. We've seen this morning a very good presentation about all those things. So we'll see how those things synchronize with other industries like avionics in this panel. So you know well that Ethernet supports service-oriented communication, seamless updates over the air updates, integration of safety critical and non-critical domains, and unified backbone. It can replace legacy bus with a scalable, interoperable infrastructure, making SDV architecture not only possible, but future-proof. So what about the avionics and aerospace industries? So we already said that the different speakers we have, Jean-François Bortolotti, Ampere from car industry, Marc Boyer Onera from aerospace industry, Kirsten Mateus BMW from car industry, and Valentin Kresmar, Airbus from avionics industry. So a little bit of a presentation of the speakers. So Jean-François Bortolotti has built a robust career in mobile telecommunication and silicon industries. He's always been interested in software technologies. He's done a lot of industries like IBM, a lot of companies like IBM, Philips, Motorola, and Intel. He joined Renault where he became the principal architect behind all connected services, and today he's software expert leader, ensuring the software strategy of Renault, which is the forefront of innovation in software-defined vehicle. So Marc Boyer is a research scientist from Onera. He has been assistant professor of Toulouse University, INP, from 2002 to 2008. As I said, he's a current research scientist in aerospace studies in Onera, here in Toulouse. And his main focus is embedded networks, avionics AFDX networks, and TSN. So Valentin Kresmar, he's aircraft communication expert from Airbus. He's also based here in Toulouse. His career started in Airbus Defence and Space, and since then he has accumulated more than 10 years of experience in Airbus commercial aircraft industry. He is currently the expert of Airbus avionics network system for the Airbus 380, Airbus 350, and the A400M. He also supervises the technology roadmap for Airbus Group. His role includes studying and developing low latency, high ability networking technologies like TSN and FDX, and physical layer like optical fiber and single pair Ethernet. So last but not least, Kirsten Matthews. So I think all the people from automotive industry know her very well. So I don't know if I need to present you, but perhaps there are some people from aeronautics that need to know a little bit of your background. So yeah, so Kirsten Matthews joined BMB in 2009. She was being the responsible for the strategy for the in-vehicle networking technologies at BMB since then. She was her who created this event in 2011. And also, she created Open Alliance to leverage the standardization of automotive Ethernet industries. He is also the writer of 2 books of automotive in-vehicle networks technologies. The first one he wrote with her former colleague Thomas Kognisider. It was entitled Automotive Ethernet. And the second book, has been written with her colleague Michael Kandel, and it's called Automotive High-Speed Communication Technologies, SerDes, and Ethernet for Sensor and Display Applications. So now that you know better what are the speakers and what is their background, we'll start with the panel. So the panel has been organized in 3 parts. On the first part, we will discuss about the state of the art of Ethernet in aerospace and automotive. In the second part, we will travel around the Ethernet layer architecture and how it's used in each industry. And the third part will be a discussion about the standardization and the future needs of both industries, aerospace and automotive. So let's begin with the state of the art of Ethernet in aerospace and automotive to find what are the synergies and the differences between both industries. I have not said, but at the end of this panel, we have some Q&A where you will be able to ask some questions to the expert here. So the first round of questions will start with where is Ethernet used today in your industry? Why is Ethernet used in your industry? What are the turning points for Ethernet adoption? And what legacy technologies are coexisting with Ethernet today? So to answer to this first round of questions, I will give the turn to Kirsten.
Okay, this is on already. Okay, I don't have slides on this. I mean, you are all here from the car industry, so I think it's probably a lot more interesting what the others have to say on this. But to my understanding, what are the key turning points for the Ethernet adoption? And in our case, it was simply data rate. So to have actually more than the existing technology we're able to sustain in data transmission. So the 100 megabit Ethernet that we started with was used for the data rate. Of course, once you use and you adopt the technology, you come up with other things that are sort of that are sort of interesting and like you have an IP address and you can suddenly locate every car in the world and connect to a server at BMW, no matter what garage it suddenly is in or what workshop it went to. But in the end, the beginning was the 100 megabit. And I also believe that now, today, it's that data rate which has the highest adoption for everybody. But BMW started 2013. I know that the major adoption for other car manufacturers came in 2021. So I think there is a large variety on car manufacturers who have adopted a lot of Ethernet and car manufacturers who are now only planning on it to be there in the future. So between the different car manufacturers, I think there's a large variety on where it goes.
Okay, thank you, Kristen. So I will ask Valentin to answer this question. So he has prepared some slides for it.
Yeah, thank you. Maybe we can move to the first slide. I think it's relevant for this question. The introduction of Ethernet and Internet derivatives on the aircraft industry, for us, it dates back to the early 2000s when we introduced the A380, which was a kind of a specific aircraft because we introduced a lot of new technologies in there. And one of them was networking, basically, and the driver for that was not so much data rate, that it was the capability to multiplex. And there was this kind of very silly picture on top, which is basically, before that, we would connect boxes, computers together with a single wire, like a very simple field bus. And it turns out that when we were developing A380, the number of boxes was increasing, the number of interdependencies between those boxes were increasing as well. And we are getting into the situation, what we call the spaghetti plate, in which we have so many cables that everything from design to manufacturing to maintenance to even the product value, which is the weight of the aircraft, which is in turn fuel burn, was too complex for us to master. And we wanted to have a solution to put more things, more data into less physical components. And so we turned out very naturally to networking, and then to Ethernet, which was already at this moment in the IT world the go-to solutions for such a need.
So you also introduce other technologies like CAN.
Yeah, so CAN is slightly different because it was there before. CAN was introduced probably on the A320, something like in the 80s. But on a very limited amount of systems, so a couple of buses on the aircraft, and the amount of buses that we had increased over the programs, and today we have this complementary approach in which the inter-system communication, so communication between different type systems, between different boxes, is ensured by the network, so which is based on Ethernet derivatives that we call the AFDX. And everything which is not between systems, but between a computer and a sensor or an actuator, and for which the amount of data is lower and the amount of subscribers is higher, would be ensured by legacy technologies that we have, which we are from aerospace, so ARINC 429 is one of them, but also technologies that are coming from other industries, such as CAN.
Okay, thank you, Valentin. So I will go to next slide you prepare, where it's a slide that can explain a little bit how the different technologies are used in aerospace, but also in other industries.
Yeah.
So somebody wants to comment this slide? First, you.
Oh, well, yeah, it's it's just my personal view how it goes. Like in the aircraft industry, we like to do our own technology. So there's all of this ARINC stuff like 429, 629, 1553 from the military world, and we like to get stuff from other industries. So we took CAN from the automotive industry, and we wanted to take Ethernet from the IT world, and we made a specific technologies for that we call the FDX, and the standard name for that is ARINC 64 part 7, which is a bit barbaric, which we are currently upgrading into a version 2 right now. And it felt quite funny to see like TSN is kind of the same dynamic, right? To take something that works quite well in the IT world and make it compliant to what is expected in the vehicle industry, more reliability, more guarantee in terms of performances and so on. And there are a lot of similarities between the two.
Mark, do you want to comment a little bit on? No. So we'll get to how the different networks are structured in a plane.
So yeah, so this is not a view about how the it's not an architecture view. Probably I'm not allowed to share architectures with you, but it's just to give you a highlight about what are the things that we need, where are the things we need to connect together in an aircraft. And a lot of it is on the left below the cockpit. There is that space that we call the electronic bay, which is basically the server room for the aircraft, which is let's say comfortable for the electronics. So it's ventilated first. It's shielded against EMI and stuff. So we like to put a lot of stuff in there. But a lot of the other electronics needs to be somewhere else. So, for instance, you have doors electronics, which obviously are in the fuselage. You have landing gear, which are below the aircraft. So those electronics are where the actual functions and sensors and actuators need to be. So you need to go to the engines. You need to go to the back of the aircraft, outside of the avionics, we have all of the systems that are supporting the passengers, which are obviously at the level of the passenger. So you have those small passenger service units when you're a passenger in an aircraft for reading light, passenger call, all of that stuff. And so that means that you need to get to a lot of different areas. And even though the brain of the aircraft is in below the cockpit, you need to reach all of those areas all along the cabin, but also to the engines, to the landing gear, to those things. So we'll get to architectures in which we try to put a lot of things at the same place, but at the same time we need to reach those other areas which are very far away.
So thank you. So I believe those areas communicate between them. So something there is some communication, critical communication between those areas, or just.
Well, this is physical view, right? So let's say that we try to separate functions into what we call domains, which are related to safety, security, for instance. So, for instance, you don't put in the same domain things that are useful for the aircraft flying and not falling down, and things that are for the passengers, which are less safety critical but still business critical, of course. So you don't put them into the same domain, but that, let's say, logical topology in terms of what is exposed to safety, what is exposed to security, and the level of care you need to put is not mapped directly onto the physical topology, right? So even though there are things that are located at the same place, like maybe the doors and the passenger service unit of the front of the aircraft are at the same place, but they are belonging to very different security domains, so they need to be segregated physically and in terms of security as well. So that's why we mapped. And the kind of the color code that is there is a kind of exemplifying this. Everything which is green is probably quite easy to handle from the pure safety and reliability point of view, and what is orange is usually the difficult stuff because it's in a difficult area, constraint in terms of environment, temperature, fire, electromagnetics are very hard to sustain. It's exposed to dirt as well. It's very hard to maintain. So this is the difficult place. These are the sizing ones, let's say.
So thanks for this quick catch-up of how avionics industry is using networking. Just one last question. So where is used Ethernet? In the orange, green, yellow part?
Where is what?
Use Ethernet.
Oh, basically everywhere.
Everywhere.
So we had one AFDX rank 664 part 7 for the avionics. So you have AFDX between the yellow part on the left and engines, auxiliary power unit on the back, landing gear. So that's for the, let's say, the avionic parts. But you use also some Ethernet buses for less critical, so not robustified Ethernet, last standard Ethernet 802.3 and 802.1. For instance, for the passenger modules today, there is a daisy chain that's serving all of these, connecting them to the brain of the aircraft as well. So basically, you have a lot of Ethernet on the aircraft today.
Okay. Thank you. So I will ask the same question to my colleague, Jean-François. Where is used Ethernet in Ampere Group?
Yes,
Or
so,
why is used in Ampere Group?
so let's start with the why here. I mean, again, as it was already said, we have a lot more data to exchange between ECUs. So it started with the volume and the need of throughput, and it was also for the different domains. So the driving assistant, the infotainment, the diagnostic, and the reprogramming were needing more larger pipes, I would say, here. So that was the first reason. And then there is all which is coming with the software-defined vehicle, which is about the service-oriented architecture. So definitely we saw Ethernet as the right answer to enable these software-defined objects here. Of course, using Ethernet is bringing a lot of interesting existing standard protocol technologies. So again, here I listed a couple there, but it starts from the protocols themselves with what they provide in terms of communication, but also with the associated security we can have with them. Of course, VLANs, firewall, proxies are needed in order to ensure we protect the different zone of the vehicle here. And existing protocol enabled also service-oriented architecture. When we talk about some IP, we talk about diagnostic over IP or even RPC calls and things like that.
So where do we stand today?
So we started with 2 ECUs connected through Ethernet, but now with SDV we have more than 6 ECUs, so it's a real backbone in the car for us that are interconnected here. Of course, this is coexisting with the different bus technology we had previously because they are still making sense depending on the communication you need to do. So CAN, LIN, LVDS are there, obviously. But we also, with Ethernet, we are also paying a very specific attention to security aspects.
So thanks. So anybody else that would like to answer to those questions? If not, we continue to next one. So next question is about which environmental regularity constraints shape network architectures? I'm thinking about ISO 26262, cybersecurity. So what shape the topologies? Does anybody want to answer this question? So yeah, and another question about topology, okay. So perhaps you can answer both questions at the same time. How is your sector approaching zonal and centralized architectures? This is a very big topic in automotive. What is driving it? What is blocking it?
I think one of the very important points, and that's also what a little bit unites the industries that are not data center is one of the point on the thermal and mechanical the constraints that you have, but also on the you mentioned here the ISO 26262, which is the SIL levels are somewhat different in the aerospace industry, but still you have these you have these requirements. And I find it interesting that on the planes you're very clear on the domain separation, and that's also where we come from in the cars. We also have the domain separation for these reasons. I mean, not so much for the thermal stuff, because I mean the car is not quite as large, right? And the thermal is varying, but also not quite as much. But on the level you need for the ASIL, you really, the requirements you have on actual functional safety is very important to separate the domains. But other than in the planes, we would sort of see Ethernet as a technology that allows to mix the domains. No, right? That is the really, for me, one of the main inventions that came a little bit by. It just happened to come with it. Yeah, as again I said, we started for the data rate and the need, but suddenly you can do something like software service-oriented architectures, and suddenly you realize, oh, I can do a lot more, and I can actually, thanks to TSN, mix different quality of service requirements, different ASIL levels, almost in one network. That is the real. That is, for me, the real magic of the Ethernet toolbox. That allows to change the architecture. That allows to develop cars differently. That really brings all the changes.
So I believe the Ethernet is an enabler of zonal and central architectures thanks to the Ethernet backbone where all the domains are mixed. So how about avionics? Are these kind of ideas being discussed, or is not really?
To a point. So let's say that what drives well, the architecture basically is not standardized. It's probably the added value of the OEMs on that. But we have those environmental standards, like we mentioned, thermal, electromagnetic and stuff, that pushes us to push as much electronics as we can in a very specific area, which is below the cockpit. And as less as we can in the other areas. One other example of which is for pushing as much things as possible into the electronic base, that when there is something to maintain, like an electronic box that is failing, if you have to dismount the seat and the panel to access the electronic box, it's very complicated, right? And it's and the aircraft cannot fly before that, which is some value loss for the airline, which is our customer. So we try to put as much things as possible into this electronic bay and as less things on the other side, which is kind of leading to some kind of zonal architecture, like some kind of HPC in this electronic bay and some gatewaying a bit further away in the aircraft. And the advent of Ethernet, and especially the fact that we have a flow-based technology with segregation between those flows and this segregation being enforced by switches, is a way for us to make sure that we can have different systems occupying the same physical topology with different safety level, for instance. And if there is a very low safety level that we don't care about and that could fail at any time, which is failing, then we can ensure that there is no impact on the biggest safety critical function. So this is also a way that we do things. At the end, we don't put anything on the same network. There are still some security requirements that needs to be fulfilled. That leads us to segregate the domain still. And so we don't share what's for the passenger and what's for the aircraft system, for instance. But for the aircraft system, there are high safety critical functions and low safety critical function. Yes, because of that approach, they can share the same physical topology.
Okay, so I have a question for Mark. So you've been working a lot with space industry, like building satellites, research projects. So are those industries approaching the Ethernet the same way? There are.
From what I know, currently not.
Yeah.
They still, so first, satellites have very small numbers of computers with regards to plane or even with cars. So the connectivity needs are quite different, and so they still have and the environmental conditions are very different. So the physical layer needs to be compatible with space domains. And there is currently not. So they currently have their solution. So I guess that if there was an Ethernet solution, they can be interested. So they have research projects but research projects are currently more okay. If we have an Ethernet hardware, one day could we use it But I think that having hardware that can fly in space in this environmental condition is really the hard point currently.
And a spacecraft, do you know if they use Ethernet anyway?
Yeah, spacecraft Ariane use use Ethernet, yes.
TT Ethernet?
TT Ethernet, yes, we can say it. Okay, they use TT Ethernet because of good property of. Spacecraft is a very simple cyclic behavior that is really that fit really well into a time trigger system like TT Ethernet. So that was, for my point of view, what I know the key point, and of course boundaries.
Okay.
Always boundaries.
Thank you very much. So we'll jump ahead to the second part of today. So we'll start the travel of the layers, communication layers, from the physical layer. Which Ethernet layer technologies make sense to deploy in your industry? So we, Automotive Ethernet developed the T1 layers in Open Alliance. 1000 base T1, 100 base T1, 10 base T1S, and the multi-gigabit T1 PHYs. So how about aircraft industry and satellite industry? Are you looking into this physical layer from the automotive?
Yeah, definitely, yes. So most of our physical layer is currently legacy stuff, so 10 base T, 100 base T. They're already quite big cables, so it's only 4 wires, but it's already quite a big cable. And if we want to move in speed towards 1 gigabit per second, that's an 8-wire cable, which is, in my opinion, definitely too big. It's too expensive. The connectic is a nightmare. It's too heavy. The bending is a nightmare as well. So we've been definitely looking with interest to the single pair Ethernet stuff. For the pure diameter and weight aspect. Usually the standard limits those usage to 15-20 meters. And obviously an aircraft is slightly larger than that, so we need to figure out what are the available remaining margins in the technology, or adapt our architecture to that if we want to make use of that. Otherwise, the alternative will be fiber optics for the supporting this speed increase.
Thank you very much. So I think we'll discuss about standardization in the last part, but I believe if we want to bring aeronautic industry to adopt these technologies, there need to be some adaptation to answer to your.
Not necessarily, because for the physical layer we want to use COTS 5, so which is of great added value for us as an industry, and the rest of it is probably a cable and contact design for which we can adapt, and the needs for standardization is lower. So this is also the interest of this kind of technology, is that we can just take it from the shelf.
I have a question to that. I mean, I understand that you would use the same PHY and then use different cables and connectors because they need to sustain different environments. But how is the qualification of the PHYs? Do you need, is the automotive qualification sufficient, or you have extra qualification programs for, say, higher frequency, higher temperature ranges, or more mechanical robustness or something, or can you actually reuse the automotive qualification?
So part of it is data sheet, for instance. So for instance, if we have a specific temperature range, we rely on the temperature range of the data sheet. When I say we, it's probably our supplier. The rest of it will be qualification, and we don't have in our industry an entity which is in charge of pre-qualifying those stuff. So we're going to qualify boxes, and we ask the box supplier to provide evidences, whether there are tests, whether there are data sheets evidences to show that they comply. With respect to temperature, it might be tricky. With respect to electromagnetics, it turns out that there is good level of equivalence between what is applicable to the automotive industry and the aircraft industry. Just usually we have to sustain lightning strikes as well, which might be tricky, but the rest of it is usually the same. So it's mostly easy for us to get access to bring those technology on board.
So are qualification constraints influencing the choice of your PHYs, or?
Well, let's say what we're going to do is to make sure that probably going to do some tests on board in an aircraft representative environment to see how those technology fares into that kind of environment. And if that's okay, and we think that our supplier have a good chance to be able to demonstrate qualification, we'll then say, okay, please use 100 base T1 for this one. And we expect they will be able to do that. But we need to be a bit more confident before that, before specifying that to them.
So now we are confident about the qualification of the PHYs. We will jump to the quality of service of layer 2. So how do you say TSN? We talk about TSN a lot in automotive, but it is taking a long time to be introduced, and not all the parts of TSN are being introduced in the industry. We've seen a presentation before today of the TSN profiles. So this question is for Kirsten. So which TSN toolbox do you think is necessary for the industry?
I mean, you said it has taken quite a while. I think one of the first implementations in the car industry from Jaguar Land Rover on Automotive Ethernet actually immediately used parts of the AVB protocols available at the time. And I think the most important one is the 1AS, so the synchronization and the timing. I think that's one of the most important TSN specifications there is, and everything you have like a stream control or everything else is optional. I would almost say. Of course, there are some more aspects that are useful and that will be used. Of course, you have the priorities, right? There's no way for me. There's no way around priorities in Ethernet when you mix and match. But everything else, I think, needs to be looked at in detail when you have it, when you're actually building your network, whether you really need it. Traffic shaping was the one I meant. That, but again, traffic shaping is one thing. I think that's one of the largest misunderstanding when you talk to people who are not like you all experts about Ethernet, is that you don't need traffic shaping when you actually have looking at a sensor, because that sensor anyway has shaped traffic. Traffic shaping is you only need when you send more than you actually, when there is a tendency to send more than you actually need at the time, because then you can shape something. As soon as you actually have a regular traffic flow anyway, you don't need to shape, you can't shape it more than it already is shaped. So, but if you have that type of file transfer or whatever in your network, you might actually, of course, use the traffic shaping.
So maybe a question for me on that side. So you make the difference between sensor data, which is already shaped, as you mentioned, and probably file transfer or other type of protocol, which is more event-based and more bursty or stuff like that. What is the split between those two types of traffic, and how is it? What is the trend for that? Are they going to stay together? Is one getting replaced by the other?
I actually think that file transfer is something that is very rare in a car. Unless, of course, you do software updates or you flash data into a car, right? Or you have a user with a mobile phone who's downloading something. But in a regular car environment, I think file transfer is relatively rare. Yeah, so the sensor data is definitely more relevant. The question is, do you have your sensor data really in the network, like radar data or something? Of course, a lot of sensors. I mean, we have hundreds of sensors in the car which have very, very little data.
So one question for you, Valentin. So Airbus has been used since the inception of the introduction of Ethernet AFDX, which is a specific QoS technology. So are you considering to go for TSN standards? Which standards are you looking at? It's like Kirsten said, synchronization, traffic shaping, but we also seen today a presentation from Mark about not only crate-based shaping, but traffic-aware shaping. So how do you see which technologies can?
So the situation in the aerospace industry right now with respect to those topics is a bit particular. So we've been having AFDX for a lot of time. And at some point, like there was TSN that was coming, and with the expectation from us that, yeah, okay, it's going to be like AFDX but cheaper because it's coming for the automotive industry. So we say, okay, let's look at that. It turns out that for what we like, what we need, TSN is not doing something significantly more. So what we need basically is redundancy, flow-based design, policing and filtering at the switch level, maybe a bit of shaping, but not necessarily, bit of priority as well, but that's it. And the main thing that TSN was bringing is the inclusion of GPTP, and this is something that we don't have because historically most of the aircraft systems are synchronous, so we don't need the need for clock distribution. And I would say that, so there is this situation where we have TSN which is coming over, and there is a space in the aerospace industry which is very much AFDX based, and this space is saying, okay, I don't need to move over to TSN because I have something that works already, and there is no significant value in changing. But there are also a big part of the industry which is, I don't have Ethernet, or I have standard Ethernet, and I need bandwidth, I need reliability, I need a bit of configurability as well, and they are very interested in Ethernet, in TSN, sorry. So it's kind of torn right between the two right now. So part of the industry will continue with FDX, the other one will turn to TSN. And I expect that the scope of what we do with those two, which is flow-based, policing, filtering, redundancy, shaping, and clock distribution, is probably going to stay around that.
So there is an elephant in the room when discussing our TSN is the complexity. TSN is often seen as a rocket science. So we have the chance today to have here a space scientist, Mark. So I will ask him, is TSN so complex?
I will say yes, but they are experts to help you. That's my job. I think that TSN came with a lot of promises. Johannes Varkas already presented it. But I think that we have to go back to Ethernet, and what is important, as we said, was high bandwidth. Okay, we will read yours, and low cost. So it's on my left, on my right. But to get real-time internet, you need something more. And I would say that first that you have to understand is that there is no single definition of what real-time is. Okay, each time I discuss with new people from new industry, I have to understand what their definition of real-time is. But to simplify, we might say that there are two main paradigms that are either time trigger real-time or event trigger real-time. Okay, and one promise of TSN is that you can do both on the same link. Okay, and TSN offers you the possibility to have on the same output port multiple flow with very different usage, command and control with very short deadline and small size, picture, video, health monitoring, and download. And even if you don't download often on the port, it's nice to be able to do that sometimes. And that's why I say it's on all on the same link, on the same output port. I would say, when I was hearing you, that TSN is a way to partition the network, but it's a logical partitioning. Whereas up to now, we were doing a topological partition. So you have multiple network from a logical point of view on the same physical network. What do we need? In fact, it really depends on what you have. What we know is that, in fact, bandwidth could be sufficient to solve a lot of problems. But when you have a lot of bandwidth, then people start to add new services on the bandwidth. So what we know, in fact, what I've learned from FDX is that what you really need to get real time, you don't need complex systems. You need limited input. That is, you need to know what is going to enter your system, and you need static routing. And once you've got that, you've got guarantees. Perhaps the guarantees are not the ones that you are expecting, but that's another point. But that's perhaps one point why there is no TSN, because TSN, there is no, people are using a TSN in a very simple way, because in fact with Gigabit Ethernet, you solve your problem, most of your problems. There is a problem of developing hardware, so I think that it takes something like 10 years for hardware developers to implement TSN. And I will say that TSN is complex by itself. It's a very huge standard and so on, and there are tricky things inside. And moreover, it's not clear what will be used by industry. So I think that each hardware provider is asking himself, okay, if I develop this feature, will somebody buy it? And it's not clear. And yes, TSN is very complex to configure. To simplify, I will say that up to TSN, you can configure a real-time network with some Excel sheet. Okay, perhaps quite complex Excel sheet, but you can do it. With TSN, it's no more possible. Or either you use only the bandwidth. Okay, if you use only the bandwidth. But if you want to have a time over shaper and CBS on the same network, you can no more use Excel. You need complex tools. So there are a lot of so there will be software providers that will help you to configure a network. But with TSN, you can no more complex configure the system with your Excel sheet.
So how would you configure your TSN network then?
You need a software. You need people designing smart, knowing the TSN bandwidth, the mechanism, knowing the interaction between the mechanism, using theory to compute real-time guarantees, and exploring state space, and giving you, oh, here is a solution, and here is another one, and here is another one, and eventually you can pick up between the different solutions, but it's now out of human brain to configure a complex network. Do you want me to present the next slide?
You can finish. Yeah.
So I say that what we know from history is that we are always a bit disappointed. Okay, always. But we still are happy. Okay, Java was a promise of. Java has not fulfilled all promises, but it gave some, and so on. So you asked me my personal prediction. So I will say that time over shaper will be deployed. Okay, because it's the only solution to get very low latency and very low jitter, and there are some industries that need that. AVB, I will not say about the future of AVB because AVB is already there. Okay. There is asynchronous traffic shaping. I don't know what is the future of asynchronous traffic shaping because from my point of view of research scientist, it's really better than CBS. It offers a lot of new opportunity, but it's complex, and I will say that it's too late. That is, once you've understood CBS, and you really need to move to ATS, that will change your way of thinking, what your change of configuring, to get some benefit. I don't know. There is an unknown one, there is a cyclic queuing and forwarding that is not really known. I don't understand why. So I've worked a lot on that, and I don't read any research paper on that. I don't hear about any industry using that. Perhaps because it's simple and it works, and people don't speak about systems that works. They speak about about systems that they are not able to make work. Okay, but perhaps that CQF is here. I think that so frame reliability will be partially deployed because the standard itself, I guess, is too complex, but we can have a subset that is useful. And I think practice will help to design what is the part. And there is a filtering that will be deployed for anybody that that have security issue and need to be able to have different level of insurance on the same network. So DALF and so on.
I have a question to that on that slide. You were saying in the first row, the only solution to get very low jitter and latency is the time-aware shaper. And what is for you a low latency and a jitter that you think we need, that you think are needed in?
I don't know what you need, but
I mean,
I think that if you want jitters below microseconds, okay, or a few microseconds, it will be hard to get such jitter with CBS or others.
I'm just thinking of a situation in a car where I need a jitter below 1 microsecond that I find hard to envision.
I cannot imagine.
And then the question is, what is the future of TAS? Because I mean, I don't see any systems either in the aerospace industry that requires that level of accuracy. So maybe in the automation industry.
And if you synchronize robots, maybe.
The point that there are people that are used to think that real time is time trigger systems, especially in industry. So the Profinet, Profibus, and so on, they mainly are time trigger system. So they will, I guess, they will move to time trigger TSN.
This is actually really great. If you sit here on stage, you can actually ask questions. All of you have to wait until the end.
Okay. So some question for this hot topic, complexity.
I got a question on the aircraft you were talking about.
Please go ahead.
So for the aircraft, you were talking about what shapes the topology is the length. And today in 1000 base T1, right, we have the class B, class A, so you get like a 40 meters. And there's also an activity going on for long reach 100 base T1, correct? What is the typical stretch in automotive? I mean, in aerospace for a network node.
So that's the longest link that we have on an A380, which is a very big aircraft. It's probably something like 60 to 70 meters.
60 to 70.
So from the electronic bay to the engine, to the second engine, because there are 4 of them, 2 of them on each wings. But we're mostly looking at applying single pair Ethernet to our next aircraft, which is going, to be what we call the single A, so small, rather small aircraft. So 40 meters is actually quite a good target. We just have to verify that this 40 meter can be achieved with our implementation rules, being electronics or the physical installation rule in the aircraft, electromagnetics, blah blah blah, all that stuff. But I mean, clear class B is looking nice.
Okay, so a follow-up question. To meet your requirements today, back to Kirsten, she mentioned about automotive qualifications. So in the US, we have SAE J2962-3 that does the PHI qualification, for example, right? The automotive standards for the North American OEMs. And also in Europe, I believe that we also have something very similar, an ISO. Are you guys looking at those for your qualification and maybe adding what you need? Okay.
Yeah, probably we'll base ourselves on this one for, let's say, the metric, like the eye diagram, like something like that, and the metrics, but we'll probably apply that. Well, we define the setup around that. We'll define probably the electromagnetic aggression you need to apply, but actually the pass-fail criteria will probably be based on what exists in the standard.
Okay, and last question. I don't want to be pessimistic, but this is worst case. Let's say 40 meters doesn't work to your qualifications with many inlines, and you said fiber optic. What speed are you targeting for fiber optic?
Let's say between 1 and 10 gigabits.
Okay, all right, thank you.
Thank you. I propose to continue because if we want to go up all the layers until software and software-defined vehicles, we need to speed up. Just 30 minutes to go. So to answer this question, Ampere will prepare also a slide how TSN is adopted in Ampere, how we see that. So I will ask Jeff to answer.
Yeah, so the main reason for using TSN in our solution here on SDV, it's due to the zonal plus central architecture here. The synchronization of the traffic is the first item, definitely. And when we have some traffics that needs to meet exact timing, and then we have the shaping aspect. So shaping is important to us to ensure that we have the right, we can protect different link from different traffic types. And after, well, the policy definitely is there. The asynchronous traffic shaping, we are looking at it. We have not seen yet a direct application or a game changer yet, but we need to continue looking into that and keep that in mind. We have not seen use case for the other toolbox, I would say here, the traffic aware shaping, the preemption, the frame replication and suppression. These are things we know, but we have not seen really the need for the use yet.
Do you have something to add, Mark?
No. That's you are. I'm looking at how it works, and you know your needs. Okay.
So here is about the TSN alternatives. If TSN disappeared tomorrow, what would you break in your stack? Which properties of TSN cannot be replaced? Synchronization, shaping, policing, redundancy, preemption. Who want to take this question?
It's a biased answer, but basically, if TSN disappears tomorrow, I'm okay. And maybe my colleague Hubert will kill me for that, but I will be okay. He probably won't. I think when the thing that we like in TSN that I look forward is probably everything linked to GPTP, and especially the new standard that Janos has opened up on earlier about fault tolerant GPTP, which fault tolerance is real. So I have a question for you from the automotive industry, whether fault tolerance in the time distribution is something that's of interest for you. But that's really something that's something that we miss today, and the rest of it we already cover with other means.
I think if you think of autonomous driving and so on, you start really to rely on the time stamping. And so to know, you really need to know how old any data is you get. And so time synchronization together with time stamping, I think that would be, you would need to design cars differently or use real-time Ethernet or some different means if that didn't exist. So that would be a fundamental change.
Yeah, I think to answer to your question, I think what is important for the automotive is not the redundancy of the GPTP, but more to know if the GPTP has failed, to go to a safe state. And this is very important, not to change to maintain the synchronization, whatever it matters, but to really know if it's not working, and then you can take actions, defensive actions to that. So let's jump up to higher layers, layer 3, 4, 5, 6, or we are going to speed up a little possible. So this is a big question. How do you ensure real-time and reliability simultaneously? Is a mission impossible? How each industry address this? If you want to have some information very fast, and at the same time you want to be sure that the information has arrived to its destination.
For me, I have the same concerns that I heard earlier. What is real time? You know, there are so many. I mean, whatever use case you look at, real time can mean something totally different. And I believe in what I said earlier. The most important thing is always to know how old data is, and that's the yeah, that's the most important one. So I think it's for me that what makes reliability.
Yeah, fully agree with that. It's mostly about what is the edge of the data and how you can demonstrate that. But I don't believe that we are facing latency and jitter constraints which are impossible to attain with the technology that we have today.
Yeah, on our side here, I mean, it has been shared earlier in some presentation. We have some use case where we are looking closely at the latency. So this is still a technical challenge given the complexity of the solutions. And we really are looking at improving the control end-to-end of the quality of service. We have mechanism at the network layers, as we discussed. This is mandatory, but we think it's a check mark. There are tools, there are functionalities, but to achieve the end-to-end latency by design, it's requiring more than that, and you are getting to the software layers, software implementation, and so on. So we are still looking at ways to secure those aspects going forward to improve the solutions.
But what are the absolute numbers of latency? I mean, if you look end-to-end latency, you typically break it down to the latency of the network. What order of magnitude are we talking about in the latency from the network you are looking at?
Like I think it was showed earlier, again, the network side is a small part, but for the end-to-end, because of all the software pieces that are in the middle, again, we are talking about the 100 milliseconds that you want to guarantee by design to a certain extent for certain use cases. And the network is a small part and is very well advanced and handled today with what we have, or at least there are solutions. After it's a matter of putting them in practice, configuring them right. But this is not the only answer we need. I mean, it's necessary, but it's not enough. So the software side need more mechanisms to control this quality of service from our perspective.
Agreed.
Let's imagine a system. You push a button and you want an action in less than 100 milliseconds.
If you have a touch screen, you want 100 milliseconds response on what you touch.
Yes, and what happens if it's very complex architecture like we showed today and you lose your message? You want some reliability, but then you lose perhaps your target to have the reactivity.
That's something I tell to students. One problem in computer science is that we have no margin. In physics, when you're designing systems, you make all your systems with your geoboard, your Excel, and then at the end you add 10% more of something as a margin. Okay. In computer science, you cannot. Margin is always 100%. Okay. So in fact, if one data is lost, okay, you need to remit it. So the solution is, if the deadline is, I will say, 100 milliseconds, and you want to have time for remission, then the deadline becomes 50 milliseconds. So you double the constraint. Or you can send on 2 networks. So each time you double. If you want to be safe for one loss, sometime, in fact, you need to double the resource. And that's a very high cost. And for avionics systems, sometimes you make 300% and even more sometimes.
But perhaps doubling is not enough, because you need to detect that you have lost your information. And that takes some time also.
Yes, but a late data is a lost data, in fact. So there is that's the point. In fact, there is a theoretical result, meaning that you cannot make the difference at some time between the lost data and the late data. So if the data is late, it's lost. So
we are coming back to the periodic messages we are using in CAN since its inception of CAN. I mean, this is the solution. We have a service communication.
But it works only like for periodic data, right? So if you have event-based data, that's not a thing anymore. And then you have to, and then you, in some functions, you may not be able to afford to lose that data, like pushing the touch screens, for instance. Like, you don't want your customer to be like that on your touch screens. Probably that's not a good outlook. So maybe you have to use redundancy for that, but I don't believe that re-emission, like TCP-based stuff, is a solution for our architectures.
Okay, thank you very much. So we can jump to the next question. So which higher layers, layer 3, 4, and middleware, are being used in your different companies or industries? Which protocols are using? Are you looking into automotive aircraft protocols, or the other way around? We are looking.
It's going to be quite quick. So basically, we have a bit of IP and UDP purely for the sake of addressing, for identifying sessions and that stuff. So basically, what Max Turner was explaining a bit earlier, and that's all.
I think on the automotive, everybody knows very much what is being used.
I think we are relatively straightforward with UDP and IP and some IP on top. Unless we tunnel, of course, CAN, then we don't use any of that. But
diagnostic over IP for other protocols. So what is the policy for introducing new protocols or middleware in your stack? If there is a new need, you look on the protocols from the industry already there, or do you?
On our side, again, thanks to the Ethernet backbone, we are, reusing a lot of things that exist on the IT systems. So in terms of protocol, this is the first place we look at. IT systems have been doing communication between systems that are already service-oriented for most of the case in modern IT software. So this is the first place we'll be looking at and see how much we can reuse off-the-shelf stack when they are applicable. Of course, in our environment, we have constraints. It starts with memory, it starts with CPU capacity and so on. But usually there is an interest to leverage what exists from this perspective. And so things like using data centers and things like that are where we're looking first.
Any comment to?
That was one of the ideas when we started with Ethernet, and we also had AutoSAR, right? So we also wanted to have something that works with AutoSAR in the end, and that led to some IP, because we couldn't get that level of middleware existing off the shelf that was suitable for us at the time.
Okay, thank you. So we will end up this part. I think Valentin prepared a wrap up, but we are running out of time, so
we can skip it. It's mostly things that I already expressed, so if we're out of time, we can skip it.
So we will jump to the last part of today, which is the standardization and future needs. So how do you define, first thing it's a hot topic in the industry, how do you define the software-defined vehicles or software-defined planes in your respective industry?
So, so I've seen that acronyms going on in Airbus these days, but it's not something that we've used a lot. I'm still unsure what it means. If it's linked to the fact that the vehicle can be updated, a lot of it is software, and a lot of its function is supported by software and hardware, which makes it easier to upgrade, fix, improve, and all that stuff. This is something that we've been introduced with the A380, so we've been doing that since a lot of time, and and we have programs like older programs which don't have that, and we see the difference between those more modern programs and the old ones when it comes to updates, offering new services, fixing stuff, improving on the fly. Like if we want to update something and you want to deploy that on an A320, then you have to catch up the more than 1,000 aircraft which are in the air, and ask them to immobilize the aircraft for 1 day, 2 days, 1 week, which is as much value lost, which is absolutely unacceptable for our customers. And if you do that on an A350, which is our latest program, it's like a 1 hour uploading of software on it to upgrade the function, which is very easy. So the value there is tremendous, and we're not going back on that.
So how it's addressed software-defined vehicle in BMV?
I recently heard a very good definition that I liked, and that said, if you update, it's a software-defined vehicle when you, by changing the software, change the characteristics of the car. That was sort of the definition. So not just bug fixes or small updates, but that you really change the characteristics of the car by changing the software. So, but of course it has also, that has a large variety of what it could be.
What do we mean by those characteristics?
Yeah, that's a good question. Maybe it drives differently. Maybe it has a different color. Yeah. So we can already change the color of the car. So that is
by software.
By software.
Yeah, I mean, on our side, it starts with, as it was said, I mean, updates and upgrades. So the fact that you don't have something that is predefined and static is something you can change. So, of course, it has been said earlier in the day, updates to fix issues, avoid getting back to the dealer is the basic, I would say. But the key point, as Carsten said here, it's the evolving of the car. So you can offer new features, new functionality to your customers after the facts, and they can also decide what they want to do, what they will be interested by. Some users, some customers will like this type of features and will be ready to buy them afterwards. Maybe when they buy the car, they don't want to buy it right away. And then after the use of the car, they see an interest of having something new and something different. And it enables also us as car manufacturer to propose more things after having sold the car. So this is really, from the customer's perspective, the driver. And after it's the software-defined, I mean, there have been software in car for some times. The software-defined aspect is how deep you can go into the car functions to make them evolve. And this is where there is a challenge there. And this is where, I mean, the SDV is from our perspective.
So if we change the characteristics of the car, do we need to upgrade the network? Do we need a software-defined networking?
I think a software-defined vehicle is a lot easier than a software-defined network, actually. So in my mind, I mean, also an in-vehicle network is so, in comparison, so small that I don't really think you change the characteristics of the network in the car by software on almost on the, I mean, not while you use it, I mean, not when the car has been out of the factory. Yeah,
So-
maybe in the design that's different. Yeah, how do you design the network for the different cars and for the different variants and so on. But actually, you might update the software of the car. Maybe you increase the safety feature in a switch or whatever, or a security update. But to really have a software that changes and that does different routing and different levels of how it comes from the telecommunications industry, the software-defined network, I'm not seeing that in the car at all.
So no central intelligence that is monitoring the network and taking decision to improve or whatever.
Yeah, then you would, if you want to improve, you need to have different options. And these different options need to have been there in hardware. So that would mean you need redundancy, you need routes you can take. You know, you can decide, okay, today there's a lot of traffic here, I go that way. But in the car, you know all these things up front where the lot of traffic is. It's not like in a telecommunications network where suddenly in one country there's a public holiday and everybody uses the phone and you need your worldwide network to do things differently, or you have your service center, a call center, that one day, one part of the day is in a certain region and another part of the day in another region, and you need to reroute those calls differently depending on the time of the day. All these things you need in telecommunications we just don't have in the car, I would say.
But don't you think like you got a new function on your car and this is requiring a lot of stuff to come to this new function already, which is pure network configuration, I mean, so probably it's a restricted definition of software-defined networking, but it is in a way as well.
Yeah, but then you would need to change the priority. So I mean, either data is important and it gets a certain amount of data and priority. I mean, for a customer, where's Max? Is he here? I mean, he always said a customer would never accept, sorry, our network is out today, we can't offer that service to you, or delay. So you need to predefine the priority of a certain type of data up front, and it's not going to change even if you put in a new function. It might need more bandwidth, but then that bandwidth needs to have been provided up front. You don't increase the bandwidth of a link with software. You only, I would say, you only increase it with hardware.
Yeah, that was an assumption from my side. So when we put out an aircraft, it's going to be out there for 40, 50 years. So obviously we provision a lot of news bandwidth at the start, so we have room to improve things. But if it's not there from the start and you don't have spare because it costs money actually to put that spare, then you cannot do that, I agree.
Okay, so thanks. So software-defined networking. Some people see it, or we've seen a lot of presentation up there about software-defined networking in the automotive those days, but there are more about changing the configuration, pre-static configuration, detecting a situation that permits to change a configuration that has already been pre-validated. So for you, is this software-defined networking or is something else?
So I'm not going to answer that question. I wanted to say something. No, I was thinking like some aspect of software-defined networking, so some abstraction capabilities of networking, like P4Es, for instance, might be a way around the uncertainty which is lying with complex technology or complex landscape of technology. So I was taking the example of AFDX versus TSN. And if you have a product that can do both, basically, because it's configurable, because its function can be adapted to different type of requirements, and it could be the case as well with various interpretation of TSN, for instance, then it's kind of a way of doing software networking and a way for people to target product line which can adapt to specific needs, but in software.
So Jean-François, you prepare a slide about software-defined vehicle. I think you already answered to it. If there is something more that you want to add.
No, I mean, just regarding the service-oriented architecture, I mean, we see for the software-defined vehicle, it's a key aspect of it, and we are looking at having it very advanced. So just want to mention the mesh network solutions with zero trust. Again, it enables us to have flexibility at the same time as still securing the solution. And of course, behind SDV, we also put virtualization that we are leveraging and simulation, hardware abstraction. So the rest, I think I already mentioned them, except the partnership with Google that Thomas mentioned this morning anyway already.
So we'll arrive to the last question. I will try to keep a little bit of time for some questions. So which parts of the Ethernet and communication stack are the most promising candidates for cross-industry standardization? After the talk we had today, is there any areas where we can have a common standard where
one simple answer to that would be probably everything that is hardware, because hardware is expensive. And we like the opportunity to reuse hardware from the automotive industry because of that, because the volumes are higher and it's less expensive for us. But again, we have some constraint to take that into account. And with respect to software, I think the value is lower, but definitely hardware. What we are doing with file, for instance, is one thing, and maybe what we're doing with hardware switches also is another example.
somebody else want to answer to this question or jump to the next one? How is your industry balance between proprietary solution and standardized legacy technologies, and what drives the decision to keep, replace, or integrate them with Ethernet?
Yeah, on our side, we've been leveraging the standard as much as we can, trying to build on what exists that answers the needs. So it starts with the needs, and software is demanding for communication and the features as well with all the driving assistance. It's a big topic. All those sensors pushing a lot of data together that need to be leveraged, used, processed. So every standard that can help us do that to answer to the customer needs is definitely of interest to us. Yeah.
Thank you. So I will jump this last question and go directly to the last question, and then go to directly to the. So if you look 5 years ahead, what single innovation, technical organization will make the biggest difference to your networks? Do you want to answer to this question?
That would mean I had a problem today that I want to solve and that I need an innovation for. And I think everything's there, actually. I think it needs to be used. And I think one of the items I heard earlier today is really, I think it was actually my colleague who said that, simplification. Yeah, we have a lot of, we're still learning and using and adding complexity, and we need to reduce complexity again at some point. And I think that's the key, how to
Very good point.
handle all the levels. So at the moment I'd say I don't need more, I need less.
Thank you.
Yeah, I will join along the complexity stuff. We're in a situation where we have different technologies which basically do the same thing, which is not a nice way to do stuff. I like that in the future, everything on the aircraft, everything networking on the aircraft is TSN based. For the moment, the landscape is has not converged enough, right? The ecosystem is not stabilized, and we're looking after maturity above everything. So definitely, when that happens, if that happens, then maybe that's an opportunity to converge to a single solution for that could be used fully over the aerospace industry.
So you prepare some answer?
Yeah, on our side, again, we are looking at communication stacks that are optimized. Again, Ethernet offer a lot of data transfer capabilities, but it comes with processing power needed just to process the data, to use it, and so on. So we see that there is room for improvement in those areas. Including the quality of service capability I was mentioning earlier, which is the end-to-end one. Network dynamic configuration, hardware and software level. As it was said, we use it today for development. So for example, we reconfigure switches to do debugging through port mirroring kind of stuff. We don't see it yet needed for now, but at some point, as it was said, we will need more flexibility. Maybe we will need it. And after, cost is a big matter to us, and integration help reduce cost. So higher integration is always welcome.
So thank you, everybody. So we'll go to the round 5 minutes Q&A. So if you have any question, if not, we will go to Aeroscopia for the networking dinner. So I think there are some questions. Ari?
Thank you. It's a good session. Thank you for presenting. I have one, not sure if it's a question, but actually, as we talked about software-defined vehicles, and I think Kirsten mentioned that whenever you want to change something, you need the ability to make sure that you want to see some changes that it's into a functionality from a customer point of view. But that all depends on making sure that upfront, you know what I'm saying, that you've thought about the processing needs and the memory. And I think that's a dichotomy here, because to say that I've got enough bandwidth, you've allocated, instead of 100 meg, you've allocated a gig, you've allocated double the memory. You need to think of that ahead. Is that, I mean, that's what, I think the key thing in terms of software-defined vehicle, I think, because you need to think of that up front to say, what are the changes that we think are going to happen in the next 5 years to make sure the platform is going to survive that long. Would you agree or disagree with that comment?
I mean, I will fully agree. Again, you can try the crystal ball stuff, but it's always a bet. So margin or provisioning in advance is one aspect, and then you are between cost increase versus promises. So it's definitely a dilemma, a difficult challenge to find the right balance. But the goal is whatever you decide at some point for your product, the software-defined aspects will open the door for you to get more juice out of it till you push it to its limit. But of course, you push boundaries, at some point you reach limits. You may spend, if it's worth it, you could spend time optimizing. I mean, software, there are always multiple ways of doing things. It requires times, effort, validation, testing, and so on. So it's not free. But if you really have value, it could make sense. So there is the value discussion of the evolution that enter into the equation. But definitely, as you said, if you don't have margin, SDV won't help you make a big difference. After, you need to keep in mind there are different use cases. Some of them may be concurrent, some not. So you still have things to do, but they need to do a difference for the user in terms of value or the customer.
Thank you.
Thank you very much for the answer. So we'll use PLCA algorithm. Go to the right.
Thank you. I guess I have to reflect to Mark's slides because I'm afraid some people would walk away with a too bitter taste, which would not make me that happy. So I think the situation is better than you explained. We are not there with TSN, we want it to be, but this applies to many technologies. I think even 5G to call one. But we are in a better shape than it was on your slide, I think. So we have hardware available, multiple vendors. I'm not a hardware vendor, but I have configured and tested some, at least 2, 3 people are in the room. So we have hardware. Complexity depends on what TSN means for you. As I was talking about it, I think nobody would have the full toolbox together. That would be complex. But it can be simpler if you go a simpler way. And there are deployments out there already. Not as many as we wanted, but there are. Like, I should have had a slide on AVB versus TSN. Some people think that TSN is replacement of the AVB. No. AVB is TSN. AVB is the early set of TSN standards. And AVB is deployed in a lot of concert halls, like just to mention one Rammstein concert, which includes industrial automation, if you will, if you think about all the liftings and things happening. And there are other industrial automation deployments as well. So we are in a better shape, I think, that was portrayed.
I agree that I was a bit provocative.
Thank you, Mark.
Sure. George Keshishian from Corning. This is a forward-looking question. You guys covered a lot. Thank you. So historically, every time transmission speeds went up and bandwidth increased, it hugely benefited the computing industry. And now with the advent of both into automotive and aviation as well, forward-looking, if you're looking to the future, what would be the top applications that would benefit from the combination of high speed and high bandwidth transmission along with high performance compute?
I mean, the autonomous driving on our side is definitely something that need more data sensors from sensors and more compute power. So it's definitely an era. And then I think it was already mentioned earlier today. It's about artificial intelligence that you can do in the car. That will again this needs more data and this needs more compute power. So those are the two dimensions looking forward I see in the automotive industry, at least from our perspective, that needs data and compute.
So will AI require more hard drive type or SSD type SAN or like storage in the cars?
We don't see that need yet, but in development, of course, I mean, autonomous driving or driving assistance, you want to record everything, you want to replay, I mean, this is definitely the game. From an customer car, not yet. We use connectivity to get data with customer approval, of course, but this is more this way than local storage for end customer.
Thank you.
I don't know on the avionics.
Yeah, this is mostly it. I would only add, but I'm pretty sure you have it as well, is everything linked to video transmission, which in terms of transmission and processing and real time is quite difficult, but it's also feeding into this autonomous driving or piloting or AI as well. It's still, all of it is there. I would add that when we're adding new bandwidths, new processing, it's just not making everything bigger. It's just that the use case that you had at the beginning that were supported by some CAN or some low speed field bus are still there. So it's just you're increasing the scope of things you have to manage. So you still have the small, very small parameters that you have to transmit. And now you have also the big stuff in the end, which makes what you need to address gets wider and more complex as a result. So I think what part of the complexity is there, not only the technology that's supported, but your ability to manage very different set of stuff.
Thank you.
So one last question, because we are running out of time, and we'll continue discussion in Aeroscopia in the networking dinner. Please go fast.
Yeah, Jürgen Scheuring from TSN Systems. So number one, I fully agree with what Janusz said. So TSN is not complex. TSN reduces complexity if you really use it the right way. So, but actually, my question, I have a big question mark. I think the sex appeal of Ethernet is to get to a converged network, right? So to have mixed criticality, safety, critical stuff, and all the other stuff on one network. My big question mark as a company that works in both fields a little bit in aerospace and automotive is if you look at the 802.1 DP profile, they have a clear answer to, I mean, if you have a mixed criticality network, then safety is the major ruling factor, right? So there's no compromise in safety. I think the aviation guys, they're nodding, yeah, that's true, but I think the same thing is for automotive. And what I'm gonna say, DP, the aviation profile has a clear answer to that, and that is time-aware shaping and redundancy, right? So, and I think the AFDX is pretty close to that. And on the opposite, the automotive profile and the automotive OEMs, all I'm talking about, they say no redundancy, and no time-aware shaping at all. And I'm just wondering, I have a big question mark in my head, why do two industries come for a very similar problem to very different solutions on that?
This is a very good question.
Okay. I think there is a lot of history. I remember I was in a conference on real-time systems some time ago, and I was discussing with somebody from the automotive industry, and what we do when we need to demonstrate the performance of our system is that we try to avoid testing because testing is expensive. So we have like tools that shows us some evidences which are really pessimistic. So it's based on network calculus and the like, and it's really pessimistic, but that avoids testing. And the guys from the automotive industry was like, okay, I just test a lot of time. And that tells me, okay, we have very different way of doing things because our constraints are probably not exactly the same. What is expected from us, from our regulations, for compliance and safety is not the same at all. So I guess even though the problem is the same, when you're looking from far away, the answer is very similar, then probably what you need to do at the end is probably slightly different. That would be my not very useful answer to that question.
Yeah. Yeah, maybe the automotive industry doesn't have the time and the money for the validation that you don't have, right? So, yeah.
Okay, thank you very much. So thank you everybody to stay here till the end. Thank you to the panelists. And let's continue the discussion to Aeroscopia. I would like just 1 second to acknowledge Kirsten to being here today in this, I believe, one of the last panel discussion in the conference she created 14 years ago, because as everybody perhaps knows, she's moving away from the in-vehicle networks industry to a new job opportunity. Or if you want to say any words, Kirsten?
This is an unexpected opportunity, so I haven't actually prepared this speech. But of course, for me, overall, I mean, I've attended every single Ethernet and IP technology over the time, and it has been so great to have all the years of seeing how the technology evolved and how the topics that were addressed and have been addressed evolved with all the effort that all of you and all of your companies have put into making automotive Ethernet happening. And this event has always been the one where this showed, and also it showed how, again, the topics evolved over time, and it's still all extremely interesting and extremely valid, and I'd like to thank you all for your participation in making automotive Ethernet happening. So thank you very much from my side that you've done all this work and that you've always attended these conferences with me together. So thank you very much.